Good afternoon. Yeah, thank you for having me. This is Euijin Kim. Yeah, it's really an honor for me to give a lecture in here, KAIST. Today I'm gonna talk about the generative AI for travel demand forecasting. So actually, I heard that you're majoring in transportation, but this is misunderstood. So this lecture is consists of the contents that focusing on the student who major in transportation, but I tried to explain details about the contents in to my best. So let's start. So today, start from my introduction, then I'll introduce what is AI research in transportation. Then we move forward to formulation and regularization. That is the important topic of AI research in transportation. So I introduce step by step for you. So first of all, I briefly introduce myself. My name is Euijin Kim, and I received a PhD in Seoul National University 2 years ago. And after 2 years of a postdoc, I started a career as an assistant professor in Aju University. And as you know, I am a fresh PhD. So I believe that we have more things to share between you and me, more than between professor and student. So I believe that my experience and my thoughts, my vision will give you some insight or motivation for you based on this lecture. Recently, I mainly studying about methodological studies. So I'm pursuing the methodological innovation at the intersection of generative AI, econometrics, and explainable AI. So this is the main topic that I study, and I mainly apply this methodology for urban transportation planning. So transportation planning aims to do behavior analysis or demand forecasting to understand the mobility of the human being. So this is my major recent publication, and that publication are mainly related to this kind of topics. So this is my research interest. And this is my short history from the graduate student until now. So I think that most of you are difficult in deciding your topic for the PhD thesis. So for me also, that is the most difficult thing, what should do for the PhD thesis. So I briefly introduce you, how can I decide the PhD thesis and how can I set the research vision for the next 5 or 10 years. So the generative AI. So when I first go to graduate school, I start studying the computer vision because at that time, my advisor said that computer vision is the future technology for the transportation. He said that, so he ordered me to do something about the computer vision. So I started learning coding. So at that time, Python is not that prevalent framework. At that time, MATLAB is the dominant framework. So I started studying MATLAB at the time. So I was struggling to implement the machine learning method to track the vehicles in the drones video. So I think it takes about 1 year to completely implement the vehicle tracking models, the very basic machine learning model for vehicle tracking in the first year of my graduate school. Then at the next year, TensorFlow is released. So I thought that is unfair because I was very struggling with the MATLAB to implement the machine learning. But after releasing the TensorFlow, anyone can implement the deep learning model at that time. So I think that, this is also unfair for me. But I realized that implementing the TensorFlow is not enough. To do the research, we should customize. We should develop the new model based on the TensorFlow. So the experience from the first year of the graduate school give me some confidence and give me some motivation to develop a new model, new or customized model for the transportation based on the AI or deep learning technique. So based on that motivation, I want to do research about the AI, but in my graduate school, we should do some projects, the government project. We call it 용역과제. So this kind of project is given by government. So I should do that for my lab and for my practical experience. So I conducted several traditional travel demand forecasting projects. So this kind of projects forecast the travel demand of the government of travel demand from the government side, and we should follow some guideline from the government side for the travel demand forecasting. And in this guideline, we should use the four-step travel demand model, but it is too restrict model. So we should follow the every step by step. Then it is impossible to do the accurate travel demand prediction. But we should argue that this is the best prediction for the travel demand. We should do that because we should follow the guideline. So at that time, I hate for the travel demand forecasting. I hate for that all kind of related things about the travel demand. But based on those hates, I published many SHI paper at that time because all the remaining time I focusing on the research fully. So even though I published many SHI paper, those papers were not related to the travel demand forecasting at all at that time. But when I should decide the research topic for the PhD thesis, I realized that this is a real research gap, right? I should address this research gap. I should revolutionize. I should innovate the travel demand forecasting using the AI technique that I studied from the first year. So I decided to make a travel demand model using deep generative model. So deep generative model is the most prevalent generative AI model. So I decided to do it, and my PhD thesis showed that it may be possible, but limited. Because at that time, deep generative model is very naive structure of the deep generative model is applied, and I confirmed that it may be possible for the travel demand forecasting, but it is very limited because travel demand forecasting require very, very high dimensional probability distribution. So I explain in detail later. So I just confirmed that it may be possible. But the most challenging thing is that we are lack of the mobility data to estimate the travel demand model using the deep generative model. But at that time, the smart car data become prevalent for the researcher. So I tried to fuse the smart car data to the conventional data set. So I found some possibility that data fusion may be the solution to use the generative model for the travel demand forecasting. And those kind of data fusion work is published after 1 year. Then last year, November 2022, ChatGPT is released, and I found that the generative AI can do anything, right? So at that time I think that, oh, this is my vision, and I should focus on generative AI to do my research vision from my PhD thesis. So this lecture is about my research vision rather than a single research topic or single research results. So I hope that you enjoy my research vision from now. So before start the talk, I want to start with a small talk. But this small talk is related to the research vision or related to the AI research in transportation. So as you see, I'm relatively young professor. So when I see someone in person, they always said me, "Oh, what's your job?" And I said, "Yeah, I'm professor." So what is your major? Everybody says to ask me. And at the time, I said that I'm majoring in transportation. So at when I said that, they always told me, "Oh, so you may be a good driver, right?" So at the time, oh, sorry, say actually I got a driving license only 2 years ago. Actually, I got a driving license after PhD. So they surprising. Oh, how should you major in the transportation? Then I said that I major in public transit, not the driver. So I major in public transit. Then they asked me like this kind of thing. So what do you think of the controversial highway project now? Or they asked me, I want to buy some house and I heard that GTX is constructed in the future. So is it good choice to buy a house in here? So I always said that I don't know. So they asked me, so why you how can you tell that you are majoring in public transit? So I realized that I want to be a domain expert for the transportation, but not now, not until now. I'm not the domain expert for transportation, but I think there is something reason that becoming a domain expert in transportation is really, really difficult because transportation consists of roadway, railway, maritime, aviation, and even if I focus on the roadway and railway, it is consists of hardware part, software part. Software part consists of policy making, planning, operation, evaluation. Even if I focus on the software parts, there are also many other domains. For example, qualitative policy design, traffic management, connected and autonomous speaker control, and so on. So this is very empirical science, and the scope of the transportation as a domain expert is too broad, right? But I really don't like that. I don't like pretending to know something that I don't know. So this is my motto in my life. So I cannot say I'm the domain expert in transportation. So I make up my mind that I'm majoring in transportation research, not the transportation. So I from that I said I'm telling that I'm majoring in transportation research. So what is the transportation research? Actually, transportation research consists of many subfield, but I want to focus on the emerging technology and methodological study because methodological study is the most generalized topic of the transportation research. So I think that the methodological study can be divided into modeling work, and the modeling work is broadly defined by supervised learning, unsupervised learning, reinforcement learning, and operation research. And I think that all of these things can be done by artificial intelligence, AI. So I'm majoring in artificial intelligence for transportation research, covering all of the methodological part with the domain knowledge. Domain knowledge for demand forecasting, behavior analysis, connected autonomous speaker control. With this kind of domain knowledge, I can make some novel things. I can make the innovative things to use the AI for the transportation research. So I define myself that I'm majoring in artificial intelligence for transportation research. So what is artificial intelligence in transportation research? So I classified it into 4 levels. So level 1, 2, 3, 4. So I know that level 1 and 2 are also important things to do. And I already published many papers related to level 1 and 2, case study and application. And now I'm pursuing to the customization level. So I pursue customizing the AI for the transportation based on the domain knowledge. And the next step, I'm not sure I can move forward to this level, but I pursue to the innovation. So innovation is something like the developing the generative adversarial network, variational encoder, this kind of very innovative method. This is the last step as an AI research to achieve. But now I'm in the customization level. So I classify the level of the AI research based on these things. So, for example, in case of the first level case study, I think that in the case study, the people who major in computer science may be better than me. I'm sure that because, for example, let's say the vehicle tracking that I conduct at the first year of the graduate school, actually, I think that if the people who major in computer science may be better than me to do the vehicle tracking job, vehicle tracking task, I think. So I define this kind of work as a case study, and some other tasks may be similar between the computer science major and the transportation major. For example, I apply the interpretable machine learning model for the travel mode choice problem. But travel mode choice problem is very well known and can be identifiable problem for all kind of researchers. So, but it is some kind of domain specific. It requires some kind of domain specific interpretation. So I think that this kind of task can be done comparable to the people who major the computer science. But I think that the research that I focus should do that. I should solve this problem much better than PhD in computer sciences. So I define this kind of work as a customization work. So what is the customization work? So customization work is based on the domain knowledge. So based on the domain knowledge, we can identify that what is the problem or issue in transportation domain and which components are important for those issues. So this is very key point that we beat the people who major in computer science. So I'm focusing on this job. So based on this idea, I'm focusing on two different perspectives. So the first perspective is formulation. So based on the domain knowledge, we define our own problem. Based on the own problem, I want to formulate novel formulation that can be addressed by AI. So that is the first part, formulation. And the second part is regularization. So regularization is a technique to streamline the deep learning model. So I make a novel regularization for the transportation specific issue based on the domain knowledge. So regularization is related to developing the loss function, developing the new running method or making new running algorithm for the AI or deep neural network. So I'm focusing on those kind of topic based on my domain knowledge. So I will introduce the formulation and regularization in this lecture that is based on that can be considered as a customization of AI for transportation research. So I use the term AI with the same as the deep neural network. So please keep in mind that. So let's start with the formulation part. So formulation. So in this lecture, I will show you how can we formulate the activity-based travel demand model using the generative AI. So formulation is the important thing in this topic, and I will introduce how can we solve this formulation or solve this problem based on the generative AI. So this is a very beginning background. So I believe that you already know about this knowledge, but I will briefly explain about the concept of the generative AI. So all models or statistical or mathematical models can be probabilistically represented. For example, the model is broadly can be divided into generative model and discriminative model. For example, discriminative model is used for classification, regression, or choice. And the discriminative model aims to estimate the conditional probability distribution. For example, P, Y bar, X, like that. So given X, they want to estimate the probability of the yi. This is a single variable. So in terms of the generative model is aims to estimate the joint probability distribution like that. So you can understand the joint probability distribution as a data generator or data simulator. So it aims to estimate the p, y, comma, x, and p, y, comma, x can be decomposed into py by x and px, like that. This is Bayes' rule, right? And recent generative AI like ChatGPT and DALL-E aims to estimate the joint probability distribution given condition. So given the prompts, the generative AI generates something, right? So they estimate joint probability distribution given condition. So this is an example of these models. For example, given the photo, if the model classify whether this is a cat or dog, it may be the discriminative model. But if the model generate the cat photo, or if the model generate the cat dog photo, it may be the generative model. But conditional generative model, if we input the Siberian Husky, the model generate the Siberian Husky's photo, and if we put the British Shorthair, if they output the photo of the British Shorthair, we call it conditional generative model. So the generative AI that I mentioned is the conditional generative model from now on. So this is clear, right? So I hope that you are clear about what is the conditional generative model. Then, traditionally, in the transportation planning, we have used the four-step travel demand model. So four-step travel demand model, the four steps are applied sequentially. This is important, sequentially. So the four-step model divide into trip generation, destination choice, mode choice models, and route assignment simulation. But in this lecture, we only focus on these three steps because it has different mechanism. So in terms of the three models, in the trip generation model, trip production and attraction is generated in each task. Task is something like the administrative district. In Korean, Eunmyeondong, Sigungu, something like that. So that is maybe task. So at first, we generate the trip by each task. Then we assign the generated trip to the destination. So in the second step, we generate the OD trip between two tasks. So this is a matrix, and this is some kind of column, right? So after we generate the OD table, origin and destination trips between tasks, then we assign the mode for each OD trips. So OD trip between tasks by each mode is the final outcome of the travel demand model. But this is official model in Korea, so we should follow the four-step travel demand model for official travel demand forecasting. But it is very naive. So it is impossible to be accurate because, for example, in the destination choice model, the government guideline suggests only using a single parameter for the destination choice. The destination choice require, for example, in Seoul, it require prediction of 424 by 424 matrix in Seoul. This is very high dimensional prediction, right? But in the official guideline in Korea, they require us to use the single parameter for the destination choice because it is the most simple form to implement this kind of model. So other researchers like me think about it. So how can we consider more diverse travel behavior? Because this kind of four-step model is based on the tasks, right? So it based on very aggregated or spatially, temporally aggregated analysis unit. So we want to consider more diverse travel behavior. We want to consider the individual taste heterogeneity about their travel behavior. And we want to predict more detailed demand, right? So this kind of aggregated model only represent the aggregated travel demand. For but we want to understand the individual, or we want to understand households' travel behavior and their movements. And lastly, this is the most important motivation. We want to predict more accurate demand, right? But this kind of naive and simple model cannot do those kind of accurate prediction. So I think that this kind of accurate demand forecasting can be implemented by AI with the big data. So based on these three backgrounds, some researchers have developed the activity-based travel demand model. It is a little advanced model over the four-step travel demand model. The motto is activity-based model is that life is sequence of the activities in time and space. So we know that the trip is required to do some activities. For example, if we go to work, and before going to work, we drop off the kids at school, and at the work during the lunchtime, we go to the lunch. Then before we returning home, we drop by the shopping center. Then we come back. So during this activity, we do the trips in between in each activity, right? So if we understand the activities well, we can naturally predict the trips, the travel demand. So this is the idea of the activity-based travel demand model, and it assumes that travel demand drives from the people's need and desire to participate in activities. So comparing to the conventional four-step model, the activity-based travel demand model consists of two parts: activity-based model and agent-based microsimulation. So we ignore this part due to the same reason, and we only focus on the activity-based model. So activity-based model is similar to the step 1, 2, 3, trip generation, destination, mode choice in four-step model. So activity-based model, I call it ABM. The ABM aims to generate the synthetic population. Synthetic population is generating the individual that perform the trips and activity scheduling. So activity scheduling make the activity schedule for the synthesized population. So activity schedule consists of where should we go, where should it go, how can we go to the destination, and when should we go, and something like that. So those kind of information is make the activity schedules. So in terms of the probabilistic representation, the synthetic population can be represented as PXZ, and the activity scheduling can be represented as PXT bar XZ, because the synthesized population do some activity, right? So given the synthesized population, we want to estimate their choice probability of the activity schedule. So the activity-based model is just aimed to estimate these two probability distribution. So these two probability distribution is make up this joint probability, the P, XT, XZ. So this is the target that we should know for the activity-based travel demand model. So P, XT, XZ indicate the joint probability of activity schedules given synthetic population. So what is the PZ and what is the PXT bar XZ? So in terms of the data, so we can represent that PXZ is a combination of individual attributes, right? Because we synthesize the population, it means that we make some individual, so that individual can be represented by individual attributes, right? So estimating this probability is same to estimating the combination of individual attributes. For example, gender, age, income, car owner. This kind of individual attribute can be represented by PXZ, and PXT bar XZ is a combination of multiple choice dimension, destination choice, time time of day choice, duration choice, purpose choice, travel mode choice for all activity. So all activity indicate that activity trip chain within a day. So for example, we do the multiple activity, commuting activity, shopping activity, gym activity, returning home activity. So we want to know this kind of multiple dimensions of the choice for all activity trip, right? So as you know, this is very high dimensional choice problem. So at that time, and then we want to estimate this kind of high dimensional choice given this kind of high dimensional combinations of individual attributes. So this is very complex problem to estimate using some using mathematical models. So with a very simplified attribute combination for the joint probability, it requires more than 1,000 category. It's slightly under than 1,000 category should be generated to represent this kind of full joint probability distribution for the travel demand forecasting. So previous study deal with it by decomposing the joint distribution into multiple conditional distribution. So as you know, joint distribution, the dimension of the joint distribution can be reduced by decomposing it into a sequence of conditional distribution. For example, if we assume that the activity is generated followed by time of day choice, followed by destination choice, followed by mode choice. If we assume that this kind of high dimensional joint probability distribution can be reduced based on this kind of decomposition. So for example, they decompose the probability of choose activity, time, destination, mode is decomposed by these things. Like based on the Markov chain property, they decompose the high dimensional joint probability distribution into a sequence of conditional distribution. But the problem is that we don't know how the people decided. So we don't know how people decide time of day, destination, mode. For example, some people decide the time of day first, then choose the destination, then choose the mode. But other people choose the destination first, then choose the mode, and then choose the time of day. So we don't know the decision mechanism, and it may be different for each people. So ultimately, we want to estimate the high dimensional joint distribution in a single way, in a integrated way, using a single joint probability distribution. So that is the goal of the generative AI. So this is a very simple task, but very, very challenging goals, right? We should estimate the very, very high dimensional joint probability distribution for travel demand forecasting. So I'm trying to estimate this probability distribution using the generative AI. That is my research goal, and this is my research vision. So I try to make the generative AI for demand forecasting, something like that. So if I input that, calculate the possibility of a man in his 30s living in Mulledong. I live in Mulledong. Mulledong traveling to Samsungdo for commuting at 10 times. So hopefully my model, given this kind of input, my model will output the probability of choosing each travel mode. For example, probability of choosing public transit, auto, and DRT. And if 30s male living in Mulledong is 10,000 people, we can predict the travel mode of public transit, auto, and DRT respectively. And this may be the time-dependent origin and destination trips by demographic groups and the travel modes. So this is my ultimate goal, ultimate output of generative AI for travel demand forecasting. So the problem is that, is it possible to estimate this kind of high dimensional distribution? So it is the fundamental question, right? So is it possible to estimate the high dimensional distribution? But actually when I when I conduct the research for my PhD thesis, I'm curious about it. So at that time, I was not sure that it is possible. But after ChatGPT and DALL-E released, and they show that generative AI can do very, very complex tests. I think their task is much higher dimensional probability distribution than the travel demand forecasting task. So I think it is possible, but how can it be possible? It's important. How can it be possible? I think there are three conditions to do that. Three necessary conditions. The first condition is model capacity. So model capacity can be written as model flexibility or model complexity, and it can be represented by number of parameters. So it indicates that how complex the task can be done by the model. So that is the model capacity. And the next necessary condition is the big data. So big data to fully leverage the model capacity. And the last condition is the efficient model. Efficient model to train the big data that fully leverage the model capacity. This is the three necessary conditions for doing some very, very complex tasks based on the generative AI. So from the ChatGPT's view, so I believe that some of you know about the ChatGPT's logic, right? So ChatGPT have a more than several billions of parameters. So it have enough model capacity, and ChatGPT have unlimited data exists in the web, right? Unlimited text data exists in the web, and ChatGPT have very, very efficient large language model called transformer, and it actually, I think this is an innovation. They use the reinforcement learning from human feedback, RLHF. So based on this kind of efficient model, they succeed in estimating the very, very complex model based on the big data, right? So these three necessary conditions should be applied to our travel demand forecasting task. So we know that we can make the very, very large model, right? It is very easy task, but the challenging task is collecting the big data. So we should collect the big data to fully leverage the capacity of the model for the travel demand forecasting. Actually, we know that mobility big data is a promising solution for this kind of things because, for example, smart car data or smartphone GPS data and all other kinds of smartphone-based data can provide the mobility big data. But the important thing is that it is incomplete. So incomplete means that travel demand forecasting requires the attribute, specifically individual attributes. For example, the traveler's age, income, household, their home location, or their work location, or their trip chain patterns, or their activity pattern. So the travel demand forecasting model require very detailed mobility pattern of the human. But the smart car data or other smartphone-based GPS data cannot provide those kind of information because due to the privacy issue, right? Due to the privacy issue, they never provide those kind of information, detailed travel pattern, detailed activity pattern, or detailed individual attribute. So I call it incomplete data. So this is incomplete data. So we can collect the mobility big data, but this is incomplete data, right? So how can we incorporate this kind of incomplete data into the travel demand forecasting? Maybe the key task to implement this kind of high capacity of the AI models, right? So this is the great important challenge of this task. And the next thing is the efficient model. So as you know, in the language model, there are very, very good models already exist in the large language model. But in the domain of the travel demand forecasting, we should develop those kind of very, very efficient model. We should develop the very efficient model for travel demand forecasting based on our domain knowledge. So that's why I emphasize the domain knowledge-based regularization and domain knowledge-based model development for customizing to the travel demand forecasting. So this is this is the two challenges we face for the generative AI for travel demand forecasting. So large-scale incomplete data. So as I said, we should incorporate the mobility big data into travel demand forecasting. But various smart mobility collect various data from different resolution and attribute. So it means that, for example, smart card data can provide all stop can provide all movement of the transient user, their activity duration, their arrival time, their travel time, and so on. But it only provides the transit user's mobility, right? However, the smartphone data provide all users the mobility pattern, but it cannot, the travel mode in the GPS data cannot be identified, right? So each data has its own pros and cons. In contrast, the travel survey data, it is small scale data, but it is complete data. It contains all kinds of details for the travel demand forecasting, but its sampling rate is too low. So it cannot be representative for the travel demand forecasting. So we know that this data set have different pros and cons. So the key to incorporate this kind of different data set into the single framework is a data fusion. So by fusing these three data sets, we should create new value for the travel demand forecasting. So this is an example of the data fusion. So as I said, HTS indicates the household travel survey data. This is small scale complete data. And PCM is the large scale incomplete data, like smart car data, GPS data, or smartphone data. So HTS collect comprehensive attribute. It contains all kinds of attributes to be used for the travel demand forecasting, while the PCM data collect large scale time space movement data, but individual attributes are unknown in PCM data, right? So the key is that to complementarily use this kind of two data's pros and cons. So for example, this is a specification of the household travel survey data, and PCM data. One is the LTE 5G data, and second one is the smart card data, transit smart card data. As you can see, they have different pros and cons, right? But we believe that if very innovative data fusion is applied to these three data sets, we can get this kind of perfect data set. So this fused data may represent more than 30% of sample rate, and it can be collected every day, and it can define any kind of spatial resolution, and it may contain individual attributes because based on the data fusion. So the cool thing is the data fusion is that it is free to the privacy issue, because fused data does not represent the real peoples, right? So it is free from the privacy issue. So this is also very promising advantage of the fused data. So actually, the fused data generation is equal to estimate the joint probability distribution for incorporating all kind of this mobility data set. That is equal to travel demand forecasting, right? So as I introduced, estimating the probability of XT and XT is equal to estimating the joint probability distribution that fuse this kind of three different mobility data set. So I start the research for the data fusion at first time. So I want to introduce one related study that is published in this journal. So I have tried to fuse the transit smart card data and household travel survey data. And household travel survey data is the small scale complete data, and transit smart card data is a large scale incomplete data. So as I said, they have different pros and cons. And I fused these two different data sets based on the adversarial training of the GAN. So GAN is generative adversarial network. That is some widely used deep generative model. And I used the conditional GAN. This is conditional generative AI, right? So I use the conditional GAN. So the GAN, generative adversarial network, consists of two neural networks. So it's called generator and discriminator. So in the view of the data fusion, the generator tried to generate the realistic individual attributes of the smart card data. As you know, the smart card data does not have the individual attributes, right? So we want to estimate the individual attributes of the smart card data by fusing it to the household travel survey data, the small scale complete data. So to estimate the individual attributes of the smart card data, we make the generator that try to estimate the individual attributes of the smart card data, and the generator try to fool the discriminator. So the discriminator is some kind of police and generator may be the thief. So generator try to fool the discriminator, and discriminator try to distinguish between the generated and real data. So the discriminator try to distinguish whether it is generated from the generator or it is real individual attributes, right? So these two neural networks are trained by adversarial training. They adversarially training of discriminator and generator. So the neural network are trained until the discriminator cannot identify whether the estimated individual attributes are generated or not. So we can train the discriminator using the household travel survey data, complete small scale data. We can train the discriminator. Then we generate the individual attribute of smart card data. So if the discriminator cannot distinguish between the generated and real one, we can say that the smart card data can successfully mimic the probability distribution of household travel survey data, right? So this is the basic logic of the data fusion. So this is a framework for the multiple data fusion using the multiple source. So the blue box indicate the smart card data and green box indicate the household travel survey data. So the generator, given the trip chain, the generator estimate the individual attribute of the smart card data, then it is evaluated by the discriminator. And the discriminator is trained by the household travel survey data, right? So if the generated individual attributes pass the exam of the discriminator, we can say that, oh, it can generate the realistic individual attributes, right? So based on this logic, we make the data fusion model to estimate the individual attribute of smart card data. So now we can get the complete sample of the smart card data. If we can estimate the individual attribute of smart card data can provide very complete large-scale information in here, right? So this is the first step for applying the generative AI for travel demand forecasting based on the data fusion. So I also applied various other techniques to streamline the model. For example, I also applied the transformer network for efficiently handling the activity trip chain information. So this is an example of the result. So this is input. So input is the activity trip chain of the smart card data. So smart card data records all of the trip chain attributes, excluding the individual attributes, right? So this is the input. Then the smart card, we estimate the individual attributes of the smart card data like that. So the individual attributes consist of age, their driver license, gender, household income, and their trip purpose. So we estimate this kind of individual attributes using the data fusion. So we can evaluate the generated individual attributes, right? So we can evaluate the generated individual attributes, whether it is matched with the true population's observed distribution. So we can compare it, but we can rigorously compare the generated individual attribute because we don't know true individual attributes of the public smart car data. So we can compare it with the small part of the household travel survey data. There is a test set. So we verify the method using this kind of visual inspection, or we can verify whether the generated attributes are spatially well distributed based on this kind of figure. We can verify the individual attribute, the generated individual attributes. And the next related study is what is about the model capacity. So I want to confirm that whether the generative AI is enough for the population synthesis and activity scheduling. Actually, this is the topic of my PhD thesis. So I want to verify the model capacity of generative AI for the population synthesis and activity scheduling that estimate this kind of high-dimensional probability distribution. So I confirm that only in a very restricted condition, generative AI can model the reasonable PXZ, XT only using the household travel survey data. So I confirm that in a restricted condition, it can do it based on the household travel survey data only. But as I said, we can use the HTS data to other mobility big data. So by doing so, maybe we can relieve this kind of restricted conditions. For example, I transform the destination choice problem into XY coordinate regression. So destination choice require the choice of 40, 100, 2, 4, 24 categories. Classifying the 40, 100, 2, 4 categories. Actually, this is the original problem, but I simplified it as a XY coordinate regression. So it is much simpler work, but it cannot capture the spatial attribute of this kind of 400 categories well. So we should relieve this kind of restrict condition by fusing the mobility big data in the future. So in this study, I just used the naive deep generative model called variation autoencoder. So I confirmed that based on the naive variation autoencoder, we can get reasonable estimate for the joint probability distribution. So for example, I verify this model using smart car data. So in this study, actually this study aims to make the synthetic household travel survey data that is equal to probability distribution of this one, right? So I verify the synthetic household travel survey data, whether it is closer to the population than original household travel survey data. So population indicate the true data set. So only regarding the public transit trip, right? Regarding the public transit trip, we know the true population smart car data. So if the synthetic HTS data is closer to the population smart car data than the original HTS data, we can argue that the synthetic and HTS data may represent the true joint probability distribution of NHTS data. So based on this kind of verification, we confirm that at least for the HTS data set, at least for the restrict condition, the generative AI can successfully estimate the joint probability distribution for the population synthesis and activity scheduling well. So this is the main contribution of this study. This confirms the model capacity of the generative AI. So that's all for the formulation part. So in the formulation part, I want to emphasize two things. The first thing is that the generative AI is enough for estimating the very, very high dimensional probability distribution that is required for the travel demand forecasting. And we need to use the mobility big data, but those kind of mobility big data is incomplete data set. So to fully leverage those kind of incomplete mobility data set, we should do some data fusion of incomplete mobility big data and complete small scale survey data. So that is the two key points of the first part. So The second part is the regularization. So I should briefly introduce about the domain knowledge-based regularization. So first of all, this is a background. So I believe that you already know about what is the modeling, but I want to emphasize again what is the modeling. So modeling, in my view, modeling can be divided into 4 key processes. The first process is model specification, and second process is model estimation. The third one is model calibration, and last one is model prediction. So model specification is a task to define the dependent variable, independent variable, and parameters, and the model form is the task in model specification, and model estimation is estimate the parameter of the model. So it is called machine learning or statistical learning. So machine learning and statistical learning are the model estimation job. And the next one is the calibration. Calibration is to modify the estimate parameter with the additional data set. So in modern machine learning, calibration is also called transfer learning. So transfer learning is equivalent to the calibration. So next thing is the prediction. That is our application of the neural network model. So we want to focus on the specification and estimation in this part, but we more focus on the estimation part. So we want to, so if we use the deep neural network or if we use the generative AI, we don't care much about the model specification because based on the many parameters, we just fit the model to the data set, right? But in the estimation part is more difficult because as you know, as as number of parameter increase, estimating the parameter is much more difficult, right? So we should do something to efficiently estimate the model parameter. So the regularization aims to achieve better estimation for the complex AI model. So that is the basic goals of the regularization. So let's see what is the regularization. First of all, I'd like to introduce about the trade-off between the explainability and the predictability. So all model has pros and cons. So from the linear regression to the deep neural network, they have pros and cons, and these pros and cons can be represented as a trade-off between explainability and predictability. For example, we can say that the number of parameters determines the extent of complexity. So complexity is equivalent to the flexibility or predictability or model capacity or number of parameters. So number of parameters determine the extent of the complexity of the model. So if the parameter is too few, so too few parameters cause underfit and it causes a low predictability. But small number of parameters provide better interpretability because we know that for example, in linear regression have the lowest number of parameters, but each parameter of the linear regression represents some interpretable meaning, some behavioral meaning in linear regression. However, if we define the many parameters, too many parameters cause the overfit of the model. So even if it can provide the high predictability, but it is hard to interpret the meaning of the parameter. So this is the trade-off between the predictability and interpretability. And the ideal solution is that the ideal model should be interpretable and predictable. So this is the ideal solution that achieves both high predictability and interpretability. And the interpretability and predictability also can be viewed as a trade-off between bias and variance. So if we just represent the test error of the model is the all general model. If we represent the test error of the error of the model can be divided into variance and bias. So this is the example of the variance and bias. So for example, this is the model with the low variance and high bias. So this is the outcome of the model, and this is a target. So as you can see, the model is incorrect, right? This is not accurate model. But the model, so maybe we can explain how to improve this model, right? So its bias is consistent. So this kind of consistent phenomena, we can say that this is interpretable. In contrast, this model may have low bias. Based on the target, it may have low bias, but we cannot explain how to hit it. How can we improve this model? So we can say that this kind of model have high probability but low interpretability. So we can understand the trade-off between interpretability and predictability as a bias and variance trade-off. So based on those concepts, this is the data distribution, and we can make 3 different models. So this kind of model is too simple model. So we call this kind of model is underfitted model. And if the model fit too closely of the data set, we call it overfitted model. And the ideal model may be this kind of robust and good fit of the model. So actually the model can have any kinds of form, right? So based on the number of parameters, the form of the model is decided. So we want to find a model that represents this kind of good fit, robust fit of the model. So the basic principle of the deep neural network is consider all possible based on the large number of the parameter. The deep neural network consider all possible specification, and based on the data, it is expected to find the optimal parameter that maximize the predicted performance. So it means that the deep neural network expect that maximizing the predictive performance can find the good fit of the model, right? But the problem of the deep neural network is that it is vulnerable to be overfitted. So deep neural network can be overfitted like that. So to reduce the overfitting, to prevent the overfitting of the deep neural network, we should do something in their running process. So in their running process, we can impose something to make them from the overfitting to the good fitting. So this is the logic of the regularization. So the deep neural network should be regularized to move from the overfit to the robust good fit. So the regularization is a technique that can prevent the overfitting in neural network to improve the performance. So the performance is mainly about the interpretability, but interpretability is not just the interpretability. The interpretability can also provide the better predictive performance in long term. For example, we call it as a generalizable performance. So the deep neural network just aim to maximize the prediction of the given data set. So given data set may be only valid for the short-term prediction. For the long-term prediction, we should know some true underlying structure of the model, right? So for the long-term prediction or for the out-of-distribution prediction, for the different form of the data set, we should ensure the interpretability to achieve the generalized performance. So interpretability is equivalent to the good fit, robust fit. So if the deep neural network can do overfit, they may be good at short-term prediction. But to achieve the good long-term prediction, they should achieve the good fit like that. So to achieve the good fit, we should improve the interpretability of the model based on the regularization. So basically, the regularization is conducted in the estimation stage. So by trading increased bias for reduced variance. So it is equivalent to by improving the interpretability by sacrificing the small predictability. So that is the logic of the regularization. So the regularization can be conducted in two ways. So we can impose additional laws for the regularization. For example, we can penalty on the increasing number of parameters, something like that, or we can revising the optimization process. So as you know, in deep learning, we optimize the parameter based on the gradient descent method. So during the gradient descent method, we can penalize some unexpected outcome in the gradient descent. So we can regularize the model in the optimization process of the gradient descent too. So I'll introduce these two parts, loss function and optimization, but maybe I can only explain you about the optimization part. So I emphasize that domain knowledge base of regularization, right? So the regularization the optimization or the loss function should be based on the domain knowledge to ensure some good properties that required in the transportation planning. So in terms of the optimization, I revised the optimization, the gradient descent, to ensure the trustworthy economic information. So the trustworthy economic information is very important property in the discrete choice modeling, in the transportation planning problem, or in the travel demand forecasting problem. So to ensure the trustworthy economic information, we should impose monotonic constraint. So monotonic constraint this is an example of the monotonic constraint. For example, if we choose the travel mode, so increasing travel cost should decrease the utility of the travel mode. So we call it, this condition is the monotonic condition. So we know that this condition should be ensured in the deep neural network. And if we ensure this condition, we can naturally regularize the deep neural network based for our ideal properties. So this work is done by my recent paper. And the other example of the domain knowledge-based regularization is the imposing the additional loss function to reduce the infeasible data generation. So infeasible data generation is important in population synthesis, the synthesized population in the travel demand forecasting. So the population synthesis basically require more diverse population synthesis while ensuring the feasibility. So feasibility indicates that if the synthesized population is the people who are parents but aged less than 10, that is infeasible population, right? So we know that we should reduce this kind of infeasible synthesis while we want to cover the minority class of the household. For example, we use a data set from some sample data set. So the sample data set tend to ignore the minority class. So if possible, we want to cover the minority class in the population synthesis, right? So this kind of two objectives, enhancing the diversity while ensuring the feasibility, is our own domain knowledge-based issue. And in my paper, I developed the loss function. I developed the loss function for the regularization to achieve the diverse synthesis population while maintaining the feasible population synthesis. So this is the second research related to this loss function based regularization. So I will briefly introduce the first part, optimization based regularization for the travel demand forecasting. So I developed the Lattice network. So Lattice network is the neural network to ensure the monotonicity constraint that I introduced, monotonicity constraint. So yeah, so this is basic idea of the Lattice network. So Lattice network segmented the effects, this segmented the nonlinear effect like this. So it estimates the nonlinear effect of the variable based on this kind of segmented effect. And this is useful to ensure the monotonicity constraint, because if we want to impose the monotonicity constraint, we should constrain each kind of segment here, right? So if we can impose the constraint for the direction of each segment, we can impose the monotonicity constraint for each variable. So this is the main idea of the lattice network. And the lattice network can consider this kind of nonlinear effect or interaction between variables based on this lattice structure. And based on the lattice structure, we can impose the monotonicity constraint with the limited number of the unconstrained condition in the optimization process. So this is the example of the constraint optimization in gradient descent. So we know that in the gradient descent, we find a value to be updated for the parameter in the gradient descent while we training the neural network. So in the gradient descent, we impose the constraint in the gradient descent to ensure the monotonicity constraint in this part. So in each segment, we impose the inequality condition for the gradient descent part. So by doing so, we can achieve the monotonicity constraint. So this is a structure of the lattice network for the monotonicity constraint. So for each variable, it pass through the layer that imposes the monotonicity constraint. Then it is maintained for all the layer until the outcome. So in each procedure, we consistently impose the inequality condition to ensure the monotonicity constraint in the gradient descent part. So this is the result that the lattice network improved the interpretability. But the one thing I want to emphasize is that this part. So why the monotonicity is effective in deep neural networks? So this is the last thing I want to emphasize you. So this is, for example, this is the true marginal utility, true functional form that we want to estimate. The black line is a true form. And this is the data set. The point is the data set. So even if the true form of the function is like that, the data set can be generated like that, right? And the original deep neural network may overfit to the data set like that, right? So the deep neural network may estimate the function of the red line for the data set, but we want to approximate this kind of true marginal utility function, right? But if we impose the monotonicity constraint, we can regularize this part, right? This part that make the incorrect sign for the effect. So we know that increasing the travel cost always decrease the utility function, right? But in this part, the travel cost rather increase the utility. The increase of travel cost rather increase the utility. So by correcting this part, we can make the red line to be more similar to the black line, right? So based on the monotonicity constraint, we can revise this kind of red line to the green line that is more similar to the black line. So this is the basic logic of imposing monotonicity to approximate the true utility function. And this kind of effect can be done in individual level. It can be imposed both population and individual level. So in the individual level, it can regularize the overestimated interaction of the DNN, deep neural network. So it helps to regularizing this kind of overestimate effect to match with the true interaction effect. So this is the example of the imposing monotonicity constraint in the optimization process. So I hope that this this helps you to understand the concept of the domain knowledge-based regularization. So I prepare a lot of the slide, but I think the time is done. So this is all of my research. So the last thing I want to tell is that this one. So I want to provide some future study related to this work. So I think that the most promising issue in the AI research for transportation may be the interpretable AI, interpretable or explainable AI. So there are many ways to make the model more interpretable. There are many ways, but I especially focusing on this kind of topics. So the first topic is that we know that the machine learning model aims to fit the data set by identifying all the correlated structure, right? But we want to know the causal structure of the data set rather than correlational structure. So causal structure is maybe equivalent to the interpretable structure. So if the machine learning model can identify the interpretable structure rather than just data fitting structure, it may be the revolutionary approach for all kinds of economics-based economic-based field. So I think that that field is called causal machine learning. So causal machine learning aims to identify the causal structure rather than correlational structure. So this is the promising part of this field. And the other field is the ad hoc interpretability. It means that developing the interpretable model for the AI. So how to identify the causal structure based on the domain-based regularization to achieve the interpretable model. So this is the also important research direction in this field. So I hope you are interested in this field, and I hope we are jointly or multidisciplinary researching for this kind of research vision. So I'm very open to joint research. So if you are interested in this kind of research topic, so do not hesitate to contact me. Yeah. So this is all of my lecture. Thank you.
Thank you, Euijin. Have any questions? Oh, yes.
Yes.
Thank you for giving us a very instructive presentation. Actually, I have a little knowledge about ABM, and I have learned four-step travel demand forecasting model when I was in university. So um, thanks to the presentation, uh, I got some knowledge about ABM. My question is, uh, have you compared two framework? I mean, four-step travel demand forecasting and uh, your suggested model?
That's a good question. Actually, to directly compare between the ABM and the four-step model, we should finish it until the last step, process 4, right? Because at that time, we can compare the predicted travel demand between the four-step model and agent-based ABM, right? But the tricky part is that the ABM is highly rely on this part, fourth step. Actually, I exclude the explanation of the fourth step, but the activity-based model still rely on this kind of agent-based microsimulation part, but it is unveiled part. But so any commercial software cannot do this part well. So maybe I did not compare between first-time model and activity-based model, but maybe it was not that better than first-time model due to this part, step 4. So other researchers mainly developing this part, but since currently the ABM is highly rely on this part. So maybe I think that this part is the key to achieve the better prediction. So yeah, I did do that, but I expect that it may be not that more accurate considering the development of the fourth parts. Yeah.
Okay, thank you.
Yeah.
제가 한국말로 질문하겠습니다.
예.
일단 그 과거 통행조사 데이터랑 스마트 카드 데이터를 활용해서 스마트 카드에 없는 그 개별 행태를 임퓨테이션 하신 연구에 대해서 질문을 드리려고 하는데, 그 제가 알기로는 겐 모델이 이미지 데이터를 가지고 새로운 이미지를 생성하는 것인데, 혹시 그러면은 인풋 이미지를 아까 전에 데이터로 봤을 때 좀 차원수가 좀 많아 보였었는데, 이미지 데이터로 넣으려면 이제 X축, Y축, 그리고 이제 색상으로 해가지고 표현을 해가지고 넣을 텐데, 그러면 차원수를 어떻게 해결을 하셨는지 그 점이 궁금해요.
Can you make the question in English and answer to this question?
Okay. Yeah. He asked that the GAN require the format of the data. The input format of the GAN should be the image. But he asked me how my GAN deal with those kind of image format for the data fusion of smart card data and household travel survey data. So that is the question, right? So the answer is that the GAN does not require the image format. Actually, GAN is available for all kinds of the data format. But the reason the researcher used the image format is that the image format is the most complex data format. And the image format can be efficiently deal with the CNN, convolutional neural network. That's why the researcher used the image format. So rather than CNN, I used the customized transformer network that can deal with the smart card dataset efficiently, like the CNN. So based on those customized transformer, yeah, I consider the smart card data, like the image format, as the ordinary GAN. Yeah. Yeah. Yeah.
How did you obtain smart card data? Because a few years ago, one of my colleague struggled to get smart card data to research. So
That's a very, very, very good question. Yeah. Actually, the law prohibit using the smart card data from 2017. I use the 2016 data. Yeah. So
Okay.
there's no way to use the smart card data from after 2017
Why is that so?
because only the government, they allow only the government institute. I don't know how. Yeah. 공공기관, they allow only 공공기관. So they exclude the university and yeah, other institutes. So yeah, we cannot use the smart card data officially. Yeah.
But that's just a Korean smart card data. You can get any card data from other countries.
Yeah, but as far as I know, it is hard to get this kind of trip chain attributes of the smart card data from the other country. Yeah.
and in your smart card data, there are subway and bus and something like that.
Yeah. It
They are
contains all kind of information in
okay.
2016.
Okay.
Yeah.
Thank you very much.
Yeah. Oh, sure.
Thanks for giving the speech. My question is, actually, I don't understand how this generative model can be used for travel demand forecasting. Because I see that the generative model can well fit the
Mhm.
distribution of data and
Right.
can generate the data, right? But to me, the generative model usually used to generate individual samples, something like this, instead of generation conclusions.
Mhm.
Yeah, so can I ask how it can be used for forecasting?
Forecasting, right?
Yeah,
So
yes.
maybe you are saying about this part. So sorry. So if we estimate this kind of probability distribution, this only predict the current travel demand, right?
Yeah.
But there are many data sets about the future distribution of this part. For example, future population trend or future household income trend or future home and work location trend, something like that. So if we input those kind of future trend into this part, we can use this probability distribution to the forecasting rather than predicting the current travel demands. So that may be your question, right? No.
So what the uh uh what was the result of the generative model? It is just some samples, right? Samples of the
So you mean that the output is just the individual travels, right?
yeah.
So how can you do the forecasting? I see. So for example, let's say that the population of the Seoul is 10 million, right? So if we generate the 10 million individual sample, it would be equivalent to the travel demand of the Seoul.
But why not just use the original data
So why
to
we
do
use
the
the original? We can just use the original data, right? I see. So if we just use the original data, we only estimate the current travel demand, current travel demand. But if we estimate this kind of probability distribution, and if we input the future trend of population or future trend of other social demographic information, we can implement the future travel demand forecasting. So that's why we estimate the probability distribution. So if we just use the data set, we can know the current travel demand, right?
yeah. Okay, I see.
I
Thank you.
hope you understand.
Thank you.
Okay.